In this video we going to learn about bipolar junction transistor, BJT. You will learn the definition of BJT, classification, processing technique, construction, and characteristics. Transistor is an electrical component mainly used for amplification and switching in an electronic devices. The invention of transistor provide wider application in electronic devices, such as smartphone, laptop, tablet, radio, and etc. Let's now learn the definition of BJT. The bipolar junction transistor, or known as BJT, consists of three doped semiconductors that is called emitter, base, and collector, and is separated by two layers of p-n junctions. The term bipolar is based on the use of electrons and holes as charge carriers in the transistor, or EHP, known as electron-hole pair. Let's now move to the classification of BJT. BJT consists of two types. First is NPN. Second is PNP. Next, we move to the construction of BJT. In NPN, we can see the arrow is pointing out, while in PNP, the arrow is pointing in. NPN bipolar transistor contains one thin and lightly doped p-type base that is sandwiched between two heavily doped n-type collector and emitter. Emitter contain higher density of free electron than in the collector. As you can see in the animation, emitter and collector contain free electron while the base contain free hole as majority carrier. PNP bipolar transistor contains a thin and lightly doped n-type base that is sandwiched between two heavily doped p-type collector and emitter. In processing technique we will learn how the BJT works. BJT has a bias arrangement for both NPN and PNP types. In both types, the base emitter junction is forward biased, and the base collector junction is reverse biased. So now we will learn the working principle for NPN transistor. In a NPN transistor, the n-type emitter region has a very high density of conduction band electrons, as it is heavily doped. These free electrons will easily diffuse through the forward biased BE junction, to the lightly doped p-type base region. A small amount of the total number of free electrons injected to the base region, which has a low density of holes as the majority carriers, will recombine with holes. As you can see, only 5% will recombine with holes. The majority number of free electrons that do not recombine with the holes are swept across into the collector region by the attraction of opposite charge collector supply voltage. Let's now move to PNP processing technique. The PNP transistor has very similar characteristics to their NPN, except that the polarities, or biasing, of the current and voltage directions are reversed. In PNP transistor, the majority current carriers are holes, and electrons are the minority current carriers. As the hole flow into the base, which is n-type, they recombine with very few electron, as it is lightly doped. The remaining large amount of hole cross the base region, through the collector region, to the negative terminal of voltage supply. Now let's go to the characteristics of bipolar junction transistors. First one is collector characteristics curves. This curve is to show the collector current IC varies with the collector to emitter voltage VCE to specifies values of base current IB. Assume that VBB is set to produce a certain value of IB and VCC is 0. For this condition both of base emitter junction and base collector junction are forward bias. Because the base is approximately 0.7 volt, while emitter and collector are 0 volt. When both of junction are forward biased, the transistors is in saturated region. Saturation region, which is a state of a BJT when the collector current has reached a maximum and is independent of the base current. As VCC increase, VCE increases as collector current increases. This I is indicated by the portion of characteristic curve between point A and B. IC increase as VCC increases because VCE remains less than 0.7 volt due to the forward biased based collector junction. Ideally, when VCE exceeds 0.7 volt, the base collector junction becomes reverse biased and the transistor goes into the active or linear region of its operation. Once the base collector junction is reverse biased, IC levels off and remains essentially constant for a given value of IB as VCE continue to increase. Actually, IC increase very slightly as VCE increases due to widening of the base collector depletion region. When VCE reaches a sufficiently high voltage, the reverse biased base collector junction will go into breakdown. And a transistor should never be operated in this breakdown region. And next characteristics is saturation. When the base emitter junction become forward bias, and the base current is increase, the collector current also increases and VCC decreases as a result of more drop across the collector resistor. When VCE reaches its saturation value, the base collector junction becomes forward biased and IC can increase no further even with a continued increase in IB. At the point of saturation, the relation IC equals beta DC times IB is no longer valid for a transistor occurs somewhere below the knee of the collector curves, and it is usually only a few tenths of a volt. Next is cut-off region. When IB is equal to 0, the transistor is in cut-off region for its operation. With the base lead open, resulting in a base current of 0. There is a very small amount of collector leakage current, which is mainly due to thermally produced carriers. Because of collector leakage current is extremely small, it will usually be neglected in circuit analysis so that VCE equals VCC. In cutoff, neither the base emitter nor the base collector junctions are forward biased. The last one is DC load line. Cutoff and saturation region can be illustrated in relation to collector characteristic curves by using DC load lines. The load line is drawn on a family of curves connecting the cutoff point and saturation point. So the bottom of the load line is ideal cutoff where IC is equal to 0, and VCE is equal to VCC. Meanwhile, the top of the load line is the saturation point. And as you can see, along of the load line is the active region of transistor operation. As the bipolar transistor is a 3-terminal device, there are basically 3 possible ways to connect it within an electronic circuit with one terminal being common to both the input and output. Each method of connection responding differently to its input signal within a circuit as the static characteristics of the transistor vary with each circuit arrangement. The first one is the common base configuration. It has voltage gain but no current gain. The second one is common emitter configuration. It has both current and voltage gain. The last is the common collector configuration. It has current gain but no voltage gain. As its name suggests, in the common base or grounded base configuration, the base connection is common to both the input signal and the output signal. The input signal is applied between the transistor's base and the emitter terminals, while the corresponding output signal is taken from between the base and the collector terminals as shown. The base terminal is grounded or can be connected to some fixed reference voltage point. The input current flowing into the emitter is quite large as it's the sum of both the base current and collector current respectively. Therefore, the collector current output is less than the emitter current input, resulting in a current gain for this type of circuit of 1 unity or less. In other words, the common base configuration attenuates the input signal. This type of amplifier configuration is a non-inverting voltage amplifier circuit, in that the signal voltages V in and V out are in phase. This type of transistor arrangement is not very common due to its unusually high voltage gain characteristics. Its input characteristics represent that of a forward-biased diode while the output characteristics represent that of an illuminated photodiode. This type of bipolar transistor configuration has a high ratio of output to input resistance, or more importantly load resistance, RL, to input resistance, Rin, giving it a value of resistance gain. Then the voltage gain, AV, for a common base configuration is therefore given as AV equals to V out over V in, equals to IC times RL over IE times Rin, where IC over IE is the current gain, alpha, and RL over Rin is the resistance gain. The common base circuit is generally only used in single-stage amplifier circuits such as microphone preamplifier or radio frequency amplifiers due to its very good high-frequency response. In the common emitter or grounded emitter configuration, the input signal is applied between the base and the emitter, while the output is taken from between the collector and the emitter as shown. This type of configuration is the most commonly used circuit for transistor-based amplifiers and which represents the normal method of bipolar transistor connection. The common emitter amplifier configuration produces the highest current and power gain of all the three bipolar transistor configurations. This is mainly because the input impedance is low as it is connected to a forward-biased PN junction, while the output impedance is high as it is taken from a reverse-biased PN junction. In this type of configuration, the current flowing out of the transistor must be equal to the currents flowing into the transistor, as the emitter current is given as IE equals IC plus IB. As the load resistance, RL, is connected in series with the collector, the current gain of the common emitter transistor configuration is quite large as it is the ratio of IC over IB. A transistor's current gain is given the Greek symbol of beta. As the emitter current for a common emitter configuration is defined as IE equals IC plus IB, the ratio of IC over IE is called alpha, given the Greek symbol of alpha. Note that the value of alpha will always be less than unity. Since the electrical relationship between these three currents, IB, IC, and IE is determined by the physical construction of the transistor itself, any small change in the base current, IB, will result in a much larger change in the collector current, IC. Then, small changes in current flowing in the base will thus control the current in the emitter-collector circuit. Typically, beta has a value between 20 and 200 for most general-purpose transistors. So if a transistor has a beta value of say 100, then 1 electron will flow from the base terminal for every 100 electrons flowing between the emitter-collector terminal. By combining the expressions for both alpha, and beta, the mathematical relationship between these parameters and therefore the current gain of the transistor can be given as where IC is the current flowing into the collector terminal, IB is the current flowing into the base terminal, and IE is the current flowing out of the emitter terminal. Then to summarize a little, this type of bipolar transistor configuration has a greater input impedance, current, and power gain than that of the common base configuration, but its voltage gain is much lower. The common emitter configuration is an inverting amplifier circuit. This means that the resulting output signal has a 180 phase shift with regards to the input voltage signal. In the common collector or grounded collector configuration, the collector is connected to ground through the supply, thus the collector terminal is common to both the input and the output. The input signal is connected directly to the base terminal, while the output signal is taken from across the emitter load resistor as shown. This type of configuration is commonly known as a voltage follower or emitter follower circuit. The common collector, or emitter follower configuration is very useful for impedance matching applications because of its very high input impedance, in the region of hundreds of thousands of ohms, while having a relatively low output impedance. The common emitter configuration has a current gain approximately equal to the beta value of the transistor itself. However, in the common collector configuration, the load resistance is connected in series with the emitter terminal, so its current is equal to that of the emitter current. As the emitter current is the combination of the collector and the base current combined, the load resistance in this type of transistor configuration also has both the collector current and the input current of the base flowing through it. Then the current gain of the circuit is given as AI equals beta plus 1. This type of bipolar transistor configuration is a non-inverting circuit in that the signal voltages of VIN and VOUT are in phase. The common collector configuration has a voltage gain of about 1 unity gain. Thus it can be considered as a voltage buffer since the voltage gain is unity. The load resistance of the common collector transistor receives both the base and collector currents, giving a large current gain, as with the common emitter configuration, therefore, providing good current amplification with very little voltage gain. Having looked at the three different types of bipolar transistor configurations, we can now summarize the various relationships between the transistor's individual DC currents flowing through each leg and its DC current gains given in the following table. Note that although we have looked at NPN bipolar transistor configurations here, PNP transistors are just as valid to use in each configuration, as the calculations will all be the same, as for the non-inverting of the amplified signal. The only difference will be in the voltage polarities and current directions. Then, to summarize, the behavior of the bipolar transistor in each one of the above circuit configurations is very different and produces different circuit characteristics with regards to input impedance, output impedance, and gain, whether this is voltage gain, current gain or power gain, and this is summarized in the table below. With the generalist characteristics of the different transistor configurations given in the following table.